Hello, everyone. This is Scott Lee, and in this presentation, I want to go over the concept of CBUSHES and whether or not we should model them with length or no length. It's a common question that I've seen throughout my experience working at multiple companies. What's the appropriate way to model CBUSHES? Um, there are many ways to do it. There isn't like a one fit all solution. So I'm going to go over some of the possible ways to model C bushes and what is typically recommended. So the three main options to model C bushes, the three main ones are C bushes with length when you just do node to node. Then you have C bushes with no length. So the C bush is created with nodes that are coincident nodes, therefore has zero length. The other option is to model the C bushes with a very small length. So it's not modeled with a relatively long length, and it's not modeled with no length, but it has a very small length, like for example 0.01 inches. And in the next couple of slides, I'll go over why I recommend one method over the other methods. And then lastly, I'll discuss the topic of why C bushes with length can become problematic, especially when you need to run a thermal soak analysis within your FEM. So I'm gonna move this guy up here. All right, I'll move it up here. Okay, so let's review the pros and cons for each of the three main options I mentioned previously. So the C-bush with length, the pro is that it is easy and convenient to model since it is simply a node-to-node creation. Uh, Now, the main cons of this is that you may induce unintended moment generations due to the moment arm, since the C-bush has a length associated with it. Therefore, you may get a possible reduction in accuracy within your FEM results. C-bushes with length, as I'll go over in more detail in the later slides, becomes problematic when you run a thermal soak analysis because C-bushes do not have the ability to expand or contract since they do not have CTEs within its element formulation. The C-bush is simply not a geometric element. It is simply just it, it's a zero-dimensional entity, as I wrote here. It's an element with a zero-dimensional entity, and it does not represent a physical material volume with geometric properties like length, area of volume that would expand or contract under thermal loading. This problem is mainly magnified whenever C bushes are modeled parallel with the structural components. So for example, think of a long shaft, which then has C bushes with length modeled at the end of the shaft to another component. That's where this specific issue gets more magnified. Moving on to the second option, C bushes with zero length. The pros are you get more accurate results as you are not imposing the artificial moment arm relative to the C bush with length. The cons are it is a little bit more cumbersome to model, i.e., it requires additional clicks and steps to model. One main reasoning is also another con is that C bushes with zero length require a local coordinate system or a vector input to know the y direction vector. So there's basically additional steps required to model zero length C bushes. Um, Now the third option is to model C bushes with a small length, i.e. 0.01 inches, just for example purposes. And this is typically what I would recommend when you do your modeling. The pros are it doesn't require a local coordinate system creation since there is a small length associated with it. And that length will define the x vector, and the y and z vectors of the C bushes will automatically be created. So you don't need to specify a coordinate system for that C bush. Therefore, less modeling work is required, and therefore higher efficiency gain during modeling. The moment arm is small due to the very small length. Therefore, the artificial moments that get generated due to the small length are minimal, and therefore not a concern. And in addition, minimizes the thermal analysis issues since the CBUSH length is small as well. So for option 3, if you assume that you're modeling in your FEM CBUSHES using an RBE3, CBUSH RBE3 modeling scheme, the recommended approach would be to first create the CBUSHES with some length, as that's the easiest way of creating CBUSHES. And then you can utilize an API to change the CBUSH length to a small value. In terms of, I write this in terms of how to do this modeling in the most efficient way. Now moving on to the next slide. So in this slide, I'll go over some examples of some CBUSH modeling schemes and what is typically not recommended versus what is okay to model. So in this upper first example here, what you see here is an example of a long shaft with a CBUSH with some length associated with it and another long shaft. This is not recommended. This may impact your thermal analysis results, and basically, you don't want to model CBUSHES with length in this manner. It's not a recommended modeling approach. And I'll go over in some more slides later why this can impact your thermal results negatively and erroneously. Now, in the second example here, what you see is an example of a shell RB3 CBUSH with some length, RB3, and a shell. In this instance, it is okay to model your CBUSHES with length, especially since when you typically model these kind of situations where the shells are fairly close to one another, inherently the CBUSH length won't be too long, just based off the fact that your components are interfacing with one another. So it will just be the distance between the midplane between the two components. And so in general, the CBUSH length isn't really that long. But in addition to that, when you have a thermal soak analysis, the CBUSHES are actually perpendicular to the two shells, right? But in a thermal analysis, the expansion of the shells are going to be in the XY directions of the shells. It won't be in the Z out of plane direction, right? And the CBUSHES are modeled in the Z direction, out of plane direction, relative to the shells. So therefore, even if you did have a CBUSH with some length associated with it, the thermal soak analysis won't really impact won't be really erroneously negatively impacted, just because of the fact that the CBUSHES are modeled perpendicular to the shells. So in this example, typically it is okay to model CBUSHES with length. I still recommend modeling it with a small length, not a large length. And like I mentioned before, you can use an API that can automate changing the CBUSH length. Once you actually have the CBUSH modeled initially with some length, you can create an API that will automate it for you to a lower length. I'm not going to go over that in this presentation. That's out of scope. That topic is out of scope for this presentation, but just FYI. So in these next couple of slides, it gets quite wordy. I will kind of just read through this here, but I will provide some further explanations on why CBUSHES with length can become problematic for thermal runs. I'm not going to read everything here. You can read it yourself if you're interested. But basically, for a zero length CBUSH behavior, if we just focus on that, for when you do thermal analysis, right? No geometric length to expand because the CBUSH has zero length, right? So when you look at the equation for the coefficient of thermal expansion and the strain equation for coefficient of thermal expansion, strain is equal to the CTE times the delta T, right? So Your delta L, which is the change in length of your element, is going to equal the CTE times L times delta T. Now, if your CBUSH has zero length, which CBUSHES are essentially a zero dimensional element, the delta L that's being calculated will basically be zero, right? So the element doesn't need to simulate thermal growth along the length because there isn't one. Um, so if I move on to this third topic here, consistency with surrounding elements. Because the zero length CBUSH doesn't contribute its own thermal expansion, the displacements of the nodes are driven entirely by the thermal behavior of the surrounding continuum elements, which do have CTE and geometry. This aligns more closely with the expected physics in a free thermal analysis where the structure expands uniformly without internal consistencies. As a result, the zero-length CBUSH produces accurate results because it avoids introducing artifacts or errors related to thermal expansion it can't compute. Its role is limited to transmitting forces based on relative node displacements, which matches the free thermal expansion of the model. So when we compare that to non-zero length CBUSH behavior, a CBUSH with non-zero length connects two non-coincident nodes separated by a distance. This can introduce complications. No thermal expansion in CBUSHES. Unlike C-beams or C-rod elements, the CBUSH does not use its length and a CTE to compute thermal expansion, as I mentioned previously. The length between the nodes is treated as a geometric reference for stiffness and orientation, but it doesn't expand or contract with temperature. This contrasts with the surrounding elements, which do expand based on their CTE and geometry. So therefore, you may have a mismatch with surrounding expansion. As the surrounding structure expands thermally, the nodes connected by the CBUSH move apart or closer together based on the thermal strains of adjacent elements. The CBUSH then applies force proportional to its stiffness. Force equals K times X, and the relative displacement of the nodes. However, because the CBUSH itself doesn't participate in the thermal expansion, the forces it generates may not reflect the physical behavior you'd expect from a member with that length undergoing a temperature change. Artificial resistance or overconstraint. The CBUSH stiffness resists the thermally induced node displacements without accounting for its own thermal growth. This can lead to inaccurate forces, stresses, or even distortions in the displacement field, especially if the stiffness is high relative to the thermal expansion. In a free model, this resistance doesn't get absorbed by fixed constraints, so it manifests as an unexpected deformations or rigid body motion errors. In short, the non-zero length CBUSH introduces a discrepancy. The surrounding structure thinks the connection should expand thermally, but the CBUSH doesn't, leading to results that deviate from the expected uniform thermal expansion. So moving on to the next slide. Why zero length is more accurate. The accuracy difference stems from the alignment of modeling assumptions with physical expectations. Zero length CBUSH. By having no length, it sidesteps the issues of thermal expansion entirely. It acts as a point connection, letting the surrounding elements dictate the thermal behavior while enforcing stiffness locally. This minimizes conflicts in a free thermal analysis where the goal is often to observe unrestrained thermal expansion or modal behavior under temperature changes. Non-zero length CBUSHES. The length creates an implicit expectation that the element should expand thermally like a physical member, but it doesn't. This mismatch causes the CBUSH to resist or distort the thermal expansion of the model, producing forces or displacements that don't match the intended physics. Keep in mind that CBUSHES with a very small length, such as 0.01 inches, can mimic similar behaviors as a zero-length CBUSH, as the length is relatively minuscule. Thus, the thermal results will not be erroneous relative to a CBUSH with a relatively larger length. So in summary, use caution when modeling CBUSHES. It is not recommended to model CBUSHES with large length. in anywhere within your model. Either model CBUSHES as coincident CBUSHES with zero length, or model CBUSHES with relatively small lengths, such as 0.01 inches to 0.10 inches. And as I mentioned before, there are FEMAP APIs that you can develop that can automate the process of creating these CBUSHES as well as changing the CBUSH lengths, so you don't need to do this manually. I don't recommend it to do it manually because if you are to model your aerospace structure uh, as a medium or fine grid model, and you want to model a lot of the fasteners in your FEM with CBUSHES, trying to do this manually is going to take a very long time. So there are APIs that can do this fairly quickly, but which is not within the scope of this presentation. So that's the end of this presentation. Thank you, and hopefully it helped. Thank you. Bye.